Chapter 5, Section 5.5. So how do rocks melt? So now we're going to look at how we actually generate magma, because we so often say, okay, well then there's magma at this place, but how are we getting magma? Because most of Earth is solid. So in this section, we're going to look at some graphs, and so you want to be able to, at the end, be able to draw some graphs showing how if you increase the temperature or decrease the pressure, which is called decompression, or add water to hot rocks, you can cause melting. So let's look at that. Okay, so how do we melt rocks? So here you're looking at a solid crystal lattice. And I want you to think about how changing the temperature or pressure could cause melting. So pressure tends to hold the lattice together. And temperature you might be more comfortable with. As you increase temperature, it causes the atoms to actually vibrate, and it can break the bonds. And so that's how you generate a liquid. But as you go into Earth, remember that both pressure and temperature are increasing. So as you go down into the Earth, pressure is increasing, which holds it together, but temperature is increasing, which is vibrating those atoms. But at some point, you might have the case where temperature is increasing greater than pressure, and that's when you can get melting. One way. All right, so how could changing temperature or pressure cause melting? So we're going to look at this, and then we're going to think about how that fits into the tectonic picture. So how does this actually relate to geology? Okay, so here you're looking at a pressure and temperature diagram. And so temperature is increasing off to the, I guess that's, to me it's to the right. I think it's to the right for you as well. And then pressure is increasing as you go down. And so we always make pressure increase downwards on these graphs because that's what's happening in the Earth. And so we think of it as, increasing downward. Okay, so you're looking at two fields. There's the solid field and the liquid field. And so basically that's saying for these specific temperatures and pressures, a rock would be solid. For these specific temperatures and pressures, the rock would be liquid, so not a rock. Okay, so it slopes down and to the right, this boundary between them, because the higher temperatures are needed to melt a rock under higher pressure. So that's what that's showing. So the position of this line, so where this line actually plots here versus over here, just say, and you would have actual number values associated with this, but that depends on your composition of the rock. So if you have a more felsic rock, it's actually going to have a line over here. It requires lower temperatures to actually melt. So now you see there are these 4 points, A, B, C, and D. So point A is in the solid zone. Point B is at the same pressure but a higher temperature, and so it's melted. C is at the same temperature as B, but at a higher pressure, so now it's solid. And then D is sitting at both, or sitting on the line. And when that occurs, you can have both a solid and a magma. Okay. Oops, sorry. Now I said that earlier. So the line slopes because of increased pressure. So how could changing conditions for a rock A, how could you cause it to melt? And so the way to do that would be, if you increase pressure, would the rock melt? It wouldn't, but if you increase the temperature, it would melt. So how could you change the conditions for a rock at point C to melt? So if you increase the pressure, it would stay solid. But if you decrease the pressure, you could actually cause it to melt. And if you increase the temperature, you could cause it to melt. Or you could do both of those things, which would put it off into this land. Okay, so what I want you to do is observe what happens when a rock at point A is heated with an increase in pressure and without an increase in pressure. So here, if we just look at a rock that's heated and you don't change the pressure. So this could be, say, a magma intruding into an area, and the rock that's already there hasn't moved, but you've brought in this hot magma next to it. That's heating up those existing rocks. and causing them to melt. So you haven't changed the pressure, but you've changed the temperature. Now, if you take a package of rocks, remember when we talked about the rock cycle and we talked about burial by layering things on top of it. So there you're putting on more and more pressure as you put more layers on top, and you're increasing the temperature because you're moving down into the earth. And so during that, you maintain a solid rock. It does not melt in those conditions, which makes sense because the interior of the earth is for the most part solid. Okay. So I want you to observe what happens when a hot rock, say at point C, is uplifted rapidly and it doesn't have time to cool off. So we call this decompression. So think about, say, at a mid-ocean spreading center as you're pulling the two plates apart. So what's happening there is you pull it apart, and so the rocks beneath it don't have, they suddenly have the rocks that were above them, they're now gone. They've been pulled apart. And so you've taken off that overlying pressure. And so you take the pressure off, and the temperature hasn't changed at all, but the pressure has gone down. And so what happens then is that leads to melting, and we call that decompression melting. And so what's happening there is it's being uplifted to the surface faster than it has time to cool off. Okay. Now this last one, it comes into play a whole lot with subduction, and this will come back throughout the semester, so you want to keep this one in mind. So here you're used to looking at this now, so your liquid versus your solid. But you'll notice there's another curve on here now, this dashed one. So when you add water to a system, so to rocks, when you add water, this actually lowers its melting temperature, and that can be as much as 500 degrees Celsius. So if you add water to an area, you don't have to change the pressure or temperature at all. So if this rock is sitting here and you just add a small amount of water, say with a subducting plate bringing water down, that small addition of water can cause the rock to melt because it's lowered its melting temperature. So this rock didn't change its pressure or temperature at all, but when you added the water, this is now the new curve that shows where you're going to have solids versus liquids. And so at that point, now that rock has melted. And so that happens very frequently in subduction zones. So here you're seeing a rock that's just restating, here's your rock at point E, you add water, changes the whole pressures and temperatures of melting, and that rock then melts. So you should now be able to draw some graphs showing how increasing the temperature, decreasing the pressure, or adding water to the hot rocks causes melting, and start thinking about how that fits into different tectonic settings.